Thank you. Welcome back from lunch. I'm talking about some performance tuning in the OpenBSD network stack. I did with a few others. And here's some stuff to understand that. Exactly. Heckling is a must. So, before we even start, a few words on the performance before. OpenBSD's network stack never was slow. PF was never slow. PF was faster than IPF from the day it got imported, so it's not like we had big duties to solve there. And well, even before OpenBSD, compared to other operating systems at that time, was always okay. Not the fastest, not the slowest, you get the idea. So why are we doing that? Because we can. If you want to replace hardware routers, like kick Cisco's ass, and it actually works pretty darn well. And we want firewalls in more places, like places that cannot do firewalling right now because they have too much bandwidth and no machine can keep up. We want firewalls in there. Second slide on why, still because we can. We want PF to be turned on in more places where we right now have OpenBSD machines that don't run PF. I have a few of these installed. And we want to save CPU cycles that can be used for other things like crypto or deeper inspection. And to come back from the question from yesterday, there's a big difference between having a machine and giving it 5 TCP streams to keep up. Of course, you easily get many gigabits in it. But in real-world internet traffic, things are different. You have many streams. You have many route looks up, no caching that works basically because all the destinations are different, many interfaces, and most importantly, smaller packets. So that is a completely different set of workload. And if you put OpenBSD, no, not in general, machines, firewalls, routers, whatever, on the internet, there's this neat thing called DDoS. So you want to have headroom, like really. Okay, before we even start tuning, we have to understand what we are doing. Randomly pushing some buttons is really not going to help you. People keep trying and they keep shooting their feet, so just don't do it. And blindly making changes in the code without understanding what you're doing is even worse. Prerequisite to network hacking is understanding mbufs. A few of you will be bored, but I hope most of you don't know that yet. Don't even think about network hacking before understanding mbufs. Fortunately, I'm going to explain them to you right now, so in about 15 minutes, you all can be network hackers. mbufs are pre-allocated buffers. They are 256 byte on OpenBSD. They used to be at 128, and they still are on some other OSs, and they suffer from that. Fortunately, we don't. mbufs come from pool. This is, the backend for that. And since I got told people understand better when you show pictures, here's a pool of mbufs. So, mbuf header is at the beginning of each and every mbuf. mbufs get chained, so we have mbuf chains. And there are 3 different kinds of mbufs, which is actually not true, it's more, but we only care about 3 here. One is holding data itself, one is external storage, and one is for packet header. I'm going to detail that. The one holding data is the easiest case. It's just the mbuf header followed by data. External data storage means the data is not put into the mbuf, but instead we have a struct in the mbuf that explains where the data is. It is elsewhere. And elsewhere is usually an mbuf cluster. mbuf clusters are just like mbufs, just bigger, and no header in front. And in our case, it's 2 kilobytes. That's big enough for an entire Ethernet frame. What I'm not saying on the slide is we now also have a 9K and here's my list, the 4K, 8K, 9K, 12K, 16K, and 64K mbuf clusters for jumbo frames and stuff. Those pools are, of course, empty and is really used, and they replace all the custom jumbo frame style allocators in our tree, which is a good thing. Yeah. So, mbuf clusters are bigger than mbufs, thus the pool is bigger, obviously. Coming back, the packet header mbuf. The first mbuf in a chain that describes a network packet always has the packet header. Contains the information of which interface it was received on, mbuf tags, I'm going to explain that later, checksum flags for checksum offloading to hardware, which is capable of that. Recently added the VLAN tag and a bit more that's not of interest here. And packet header mbufs can contain data as well or point to external storage. So you don't have to change the second one to get that. This structure describes a complete mbuf. I know it's a big joy to look at that. So since pictures work better, I have a few more. One mbuf. Oh, actually, I of course took one with me. Traveling with mbufs gets you into trouble with airport security. I didn't expect that. They just couldn't make sense of it, so they thought it would be drugs or whatever. That works. So that's, again, our easiest case. This would work for a TCP egg or something that's really, really small. So you just have the one mbuf, the header, the packet header, and the data. A pretty uncommon case. An mbuf with a second mbuf, where the second is just more data storage. And the most common type we see is the mbuf pointing to an mbuf cluster. Of course, the mbuf cluster is so big that it doesn't fit the slide. I'm sorry for that. And even for small packets, we usually see that setup, even if the data would fit into one mbuf, because most network cards only have one RX ring, and this is filled by mbuf clusters. I'm going to explain that later in more detail. And the little data area on the bottom of the packet header mbuf is usually left unused. I'm not even sure whether it's valid to use that. So, now that you understood mbufs, we can travel. And we'll take the famous route of a packet through the system. Few words beforehand. I assume Ethernet, IPv4, and no encapsulation of any form, which means no IPv6, which sucks anyway, no VLANs, no PPPoE, no IPsec, and none of the other crap. So, fasten your seatbelts and everybody ready for takeoff, I hope. First, a packet is received by the network interface card. Actually, I have to change my notes. I'm not explaining how the RH ring is filled here. It's a separate topic. So, the packet is received by the network interface card. The network interface card DMAs the packet into the RX ring, which is a RAM provided by the driver. This assumes a NIC built in this century. There were old ones that were way, way worse, that didn't do DMA, and they're still really sucky and stupid NICs, but they at least do DMA now. And as I mentioned before, the RX ring is usually built from mbuf clusters. We ignore jumbles for now here, and details differ a lot between drivers. So let's look at the simple case, and that's just that. One single RX ring built from mbuf clusters. When it's done so, DMA the data into the RAM. It interrupts to notify the CPU that, well, there's a packet. And in reality, the better network interface cards don't interrupt per packet, but for a bunch. But again, details differ. So, the CPU runs through the list of asserted interrupts, and sooner or later, depending on what other interrupts are waiting, calls back into our register driver. So we end up in our NIC driver. There, we shovel the packet to either inputs, with the pointers to the interface the packet was received on, a pointer that is basically never used, because no driver figures out Ethernet data itself, and the mbuf from the RX ring. So if you paid attention before, you know that it's not an mbuf, but an mbuf pointing to an mbuf cluster, of course. Either input does some Ethernet magic that I don't want to care about here. And eventually figures out it is IPv4, queues our nice mbuf in the IP inter queue, and asserts a so-called soft interrupt. And the CPU is done with all hard interrupts. Just before switching back into userland, it handles soft interrupts. So we end up in a function called ipinter, which dequeues the oldest packet in the IP interrupt queue and goes to IPv4 input. Unfortunately, that has many locking issues and slows it down a bit, but we'll skip that here as well. IPv4 input does a lot of magic, so I'm just picking the major points. It has to validate the packet. So before even looking at the IP header, we should make sure that the packet's actually long enough to contain an IP header, stuff like that. It calls PF to do the inbound filtering, does multicast, broadcast, and all the other checks for IPsec, VLAN, I think, yeah. And then there's a point that looks easy. Figure out whether the packet is for us. This is actually horrid. Basically, it's walking a linked list of all local addresses and compares whether the destination is in that. We'll fix that eventually. If it figures out that the packet's not for us, it eventually calls IP forward. Otherwise, it proceeds with a local delivery or drops the packet. Local delivery is not being looked at here. IP forward obviously has to do a route lookup to figure out where to send the packet to. It does the ICMP redirect games if required, and eventually calls IP output. And there's one thing left to do. If IP output fails for some reason, it handles the generation of ICMP errors. IP output does a lot of stuff which is only of interest for locally generated packets that I'm skipping. It's a very long function. I now understood why it looks like it does. That said, I ignore here. It does the MTU magic, including path MTU discovery, fragmentation if required, but well, who cares about fragmentation? It's all 1500 anyway, and everything else just doesn't matter. It doesn't matter. It doesn't matter. Repeat. Magic for multicast, broadcast, IPsec again, we ignore that here. And finally, another call to PF test to do the outbound filtering. So, packet departed. IP output finally calls the output routine for the registered interface. Beta is different on hardware, we don't care. It basically makes the network interface card send out the packet and, yeah, ignore details. Someone, it interrupts the signal completion, and we're fine. So, we arrived. Questions so far?
Yeah. Does OpenBSD have support for cards that have multiple rings?
Yep.
Okay.
That's it. Okay, so we go on. Now we start on performance. Of course, I start with low-hanging fruit, because I just need to give you something before we get muddy again, and I have to explain a lot. Well, really easy to we skip recursing into IPsec layer if the system doesn't even use IPsec. There fortunately is a single flag to check. That's a 10 lines code change, and at least gives some 5% increase in forwarding performance. So that's very nice. Next thing, stealth firewall. There's your Dallas picture, by the way. Years ago, one of those idiots who believes in stealth, invisible firewalls. If they're invisible, you don't need one, right? Anyway, so he found a way to detect an OpenBSD bridge running PF by sending a packet where the protocol checksum was invalid, and if that would be dropped by OpenBSD by the PF, it would, and the rule set was configured to send back returns or RSTs or whatever. It would do so while the end host would silently drop the packet because the protocol checksum would be invalid. So that's a way to detect an invisible OpenBSD system in between. Well, great. The solution we had in PF for a long time is to check the protocol checksums for each and every forwarded packet. Yeah, that's kind of expensive, but it was like that for years. So my fix for that, we ignore the protocol checksum unless we actually send an RST or an ICMP unreachable back, and check the checksum then. And if it's invalid, we decide then to not send back anything, which means we don't do the checksumming for regular forwarded packets at all anymore. That gives 7 or 8% increase, so that's kind of nice for little work.
What do you lose then?
Fun?
What do you lose by doing this?
Nothing.
We defer the check until it actually matters.
Exactly.
Well, but you are going to forward a packet though that could be corrupt.
No.
Yeah, sure. But you're supposed to.
You went to end.
No, I got it, right. Okay.
Yeah.
So, time is valuable, we all know that. Getting the time on machines is actually not all that simple and cheap as we might wish. The worst case is an i386 which just has the plain old clock chip, so getting the current time there is surprisingly expensive. We had some machines that got about 20% faster by just turning ACPI on, because then you have the ACPI timers. Wasn't it like that? 20%? That's
even more than that.
hilarious.
Yeah,
But even more.
Yeah, because HPEC can run at gigahertz speeds, whereas the old clocks run at 200,
Yeah. So,
20 even.
we used to timestamp pools when we put stuff back. Every time we're done, well, pool put is basically analog to free, right? So, and every time we were putting stuff back into the pool, we were timestamping the pools, and well, nobody really knew why. I think you did the change, right?
Yeah. We just deleted it.
So we just removed the timestamping without any consequences, right? Do you remember what the speedup was?
That was, I don't know the numbers. No. It was a lot. It was
Roughly?
It was double-digit percentage.
Okay,
20%.
two-digit percentage. Nice for dropping something that's just not necessary. Kind of in the same boat, the recurrent random pool, that's the backend for all our random number generators, was stirred once per packet. Stirring requires clock reading, so we are back to clock reading. Solution, we stir once per interrupt instead of once per packet, and that gave a really nice boost as well. I don't remember the number, but it was massive. So, PF memories. Since we traveled to the system, and you of course paid attention, you know that we call PF twice, once for inbound filtering and once for outbound filtering. PF needs to remember some stuff between those two invocations, which would be the QID for alt Q, which in the end is used outside of PF, tag in the sense of the tag and tagged keywords, so you can build trust relationships between interfaces or something. The routing table ID for the multiple routing table stuff that I'm not going to detail here, that would be a complete other talk. Loop prevention for route to, some magic for the early congestion notification stuff, and well, other flags, ignore. The information for that used to sit in mbuf tags, I mentioned them earlier, which means I have to explain mbuf tags now. So, when you travel, you give away the luggage. Surprisingly, you sometimes get it back at the destination.
Not very often, though.
Pardon?
Not very often.
Not very often, no. That's why you only take hand luggage.
Not at Alitalia, for example.
Yeah, Italy, don't know. So, the airline attaches a label to your luggage for their own internal use so they can track it. And that's basically exactly what an mbuf tag is. We attach some kind of tag or label to our mbuf, to the packet header mbuf to be precise. There can be multiple tags that form a queue, and an mbuf tag is really just a struct with the list pointer magic stuff, the ID, so you know which kind of mbuf tag it is, the length, and then just followed by data. So far so good, is simple, sounds simple, it's easy to use, everybody loves it, but well, obviously the memory where these tags sit in has to come from somewhere, and since it's non-constant size, we use malloc.
Not pool.
We don't use pool.
Why not?
Because of, yeah, non-constant size. Well, actually, we talked about that. We could optimize that by just taking the biggest one and waste memory otherwise, but you'll see why it's not required anymore. Since malloc is not exactly simple, that turned out to be our performance bottleneck. It will not be your performance bottleneck. Don't even think about bypassing malloc in your own userland software. Many people tried, they all failed. Don't do it. This is not your bottleneck. If it is, you did something very wrong. So please don't do it. So, solution, instead of putting the PF stuff into an mbuf tag, we just stuff it into the mbuf header directly. To not waste too much memory, I removed some of the stuff that was in there previously that was used in a cache style, which doesn't pay out anyway because recalculating is actually cheaper than the memory bandwidth we waste by writing and reading it. There's the struct that we attach to the header of every packet header mbuf. And you see the stuff is in there from our previous list, the routing table ID, the queue ID, tags, flags, and the counter for the PF routed packets to prevent loops. Benchmarking the change, tested up in the middle, like the victim, a dog slow circus, which really has sucky network interface cards. run as a bridge, because then there is no queue and no dropping. It's perfect for benchmarking. It sucks in real life. A single pass rule and a single TCP connection through it. Before the change, the little box managed to do 28 megabits. Afterwards, it was 56. So this is kind of impressive because the performance doubled. That's it pretty much for the low-hanging fruit, unfortunately. To gain more, well, other fruit is yummy too, as said, but it requires more work, and more work namely means redesigning. The first victim of the redesigning is the PF state table, which I have to explain now. As you might have heard, PF is stateful, as in it tracks connections. Kind of obvious for TCP, for UDP, state is faked, for ICMP, state is faked, and for everything other as well. Basically, you just look at the addresses and ports if they're there, stuff like that. We want that for security reasons, so we want to know which connection the packet belongs to. We want to verify the TCP sequence numbers, last not least. But it's also way, way, way faster. The state table lookup is way faster than traversing the route set. Comparing that with the transatlantic travel, the route set traversal is a boat, and the state table lookup is an airplane. The difference is really big. Network address translation and interface-bound states complicate matters a lot. NAT changes addresses, obviously, and interface-bound states take precedence over floating states. So, state table used to be pretty flat. Each entry in the state table had 3 addresses to account for NAT, which is the reason for the you can only apply NAT outbound and redirect inbound thing in PF, because, well, we only have 3 addresses, so only one is allowed to change. There was a global state table, and then there was one for each interface to make sure that the interface-bound states take precedence. And of course, you had to consult the interface-bound state table before looking at the global one, and nobody halfway sane uses interface-bound states, so it's just really a waste of CPU cycles. There's actually one exception where interface-bound states make some sense, but I'm not going to tell you about that. So, first step, we split the state into state key and rest, where state key is the key fields that are used to find a state, which are the addresses, is that on my next thing? Yeah. Which is the address family, like IPv4 or other crap, the protocol, the addresses, and the ports. Just those things.
Are those the lookup fields?
Pardon?
Are those the lookup fields?
Yeah.
What is it? Is it a red black or something?
It's a red black tree, yeah. The state table is a red black tree. So each key holds a queue of states instead of just one, and each state points back to its key. Okay, picture. You have the state key, you have the actual states, and you have the state item linkage. In this setup, you actually could put the queue magic into the state itself, but that will change, and to not confuse you too much, I already split it. So, pretty obvious, I hope. This now means that we can kill the extra state table per interface, because we can have multiple states per state key, and colliding state keys were the problem in the first place, right? Because the interface bound and the floating one could have identical keys. Now, no problem anymore. They just hang off the same state key. To make sure that the interface-bound states always take precedence over the floating ones, they're just inserted at the queue head all the time. And the floating ones are always inserted at the queue tail. So we are sure that each and every interface-bound state is in front of a floating one. And all you have to do when looking up a state is to check that the interface pointer on the state equals your interface pointer, or there is none. There is none means it's floating.
That's cool.
The splitting off of the state keys already has a nice side effect on cache locality. So just due to the smaller structure and it being split off helped performance quite a bit. So that gave a good performance boost. I unfortunately forgot the number, but it was something in the 10% range. Yeah, more interesting stuff was waiting, so we didn't spend all that much time recording our benchmark results. We benchmarked, it's faster, go on, more interesting stuff to do. Then we had the N2K8 network hackathon in Japan, where Ryan and I finally got around to implement our new world order state table stuff. And first goal, get rid of this pretty annoying 3 address in the state key thing that nobody halfway sane could follow. In the new world order, the state key just has 2 addresses, source and destination. And since source and destination get swapped depending on the direction you look up, you just call them address 1 and 2. That avoids a lot of confusion. And same thing for ports. Each state now has 2 state key pointers. Well, since there are only 2 addresses left, we don't have space for the third address for NAT anymore. So each state gets 2 state keys, potentially at least. We call it wire side and stack side. Wire is as we see the packet on the wire, and stack is after PF is done with it for the inbound case or before PF touches it in the outbound case. It's probably easier to understand when you look at some XFIG porn again. Basically, what happens, IPv4 input, calls PF, PF is done, gets back IP forward, IP output, gets into PF again, and packet leaves. And the border between wire side and stack side is just in the middle of the PF invocation. That's our setup for the state without NAT. You see our state key, which is simple now. You see the state item. Well, since there could be multiple states still, we now need the item. And the state itself has these 2 pointers, the wire side state key and the stack side state key. And they both point back to the same state key. In the case of NAT, the wire side state key and the stack side state key pointers are different and point to different state keys. So checking for NAT, whether to apply NAT or not, is now as simple as comparing those pointers. You don't have to deal with any addressing comparisons anymore.
That's cool.
Helps a lot.
Yeah.
For this to work out, I have a hard time explaining that. It took us hours to figure it out. So for this to work, state operations like searches, insertions, and deletions done from the stack side, like from the inner side, must use the addresses on port swap, because otherwise, when we do the lookup for the return traffic, it would not match. It took us a long time to understand that and get up with that. Yeah, we drank lots of Japanese goods afterwards to recover. And for the moment, please just believe me, it's right. If you want, take a whiteboard and do what we did. And one thing.
Is that slack size?
Pardon?
Slack size? Is that what it is?
No, it's supposed to be stack size. One thing I have to point out: no computer diagram is complete without a cloud. So we had one. So I lost track. State key linking. By definition, for a forward connection, the stack side key on the inbound side must be the exact opposite of the stack side key outbound. Because we do the lookups reversed from the inside, they have to be the exact opposite, by definition. Exception only if there's some form of encapsulation, tunneling and stuff, but that is actually kind of easy to handle. So, idea, if we can form a relationship between those two, and we can because they're the exact opposites, and remember somehow the key we used on the stack side inbound, we don't have to do a lookup on the outside anymore, because it's by definition the exact reverse. We just have to establish the relationship, which is not as trivial as it sounds, but well, we did it anyway. XFIG point again for that. We just extend the state key with the reverse pointer, which points to the state key that, as said, just has everything swapped. Address is swapped and port swapped, and otherwise is identical to the other one. The rest didn't change. So, back to mbufs, because that's where we're going to stuff our information. Remember the packet header mbufs, where we stuffed our PF structure in? That still contains the header and the routing table stuff. And yeah, well, we just added something else, the pointer to the state key that we use inbound. Pardon? Yeah, it's void because this stuff still has to compile when PF is not compiled into the kernel. That unfortunately makes the code a bit ugly, but casting bullshit. No way around that. So, inbound, when we're done with PF, we just put the pointer to the key we used stack side into the mbuf packet header. Then the mbuf travels to the system, IP forward, all that stuff, and eventually it ends up in the PF test invocation on the outbound side. And finding the state that was the kind of expensive operation on the state table before is now really simple. We just check for the direction to the outbound, whether the state key is set, and whether that's the casting I'm talking about, that's kind of annoying, and whether the state key has a reverse pointer set up. If so, just use it, otherwise fall through and do the regular lookup. Which means outbound for forwarded connections, no more state table searches. Then I did benchmarks, and well, it's like 10% faster, but yeah, that was really frustrating because I expected way more from that. So, what do you do with frustration? I go for biking. That helps. Looking at the results sober. I can do that. Some people don't believe it, but I can do that. A sober look on the results. 10% is actually a lot, and we always knew that this linking is the groundwork and the foundation for many other stuff we wanted to do. So it even would be good if it didn't have any performance impact or gain. And given that, giving us 10% extra is nice. So time for optimism. As said, with that, we have a notion of flows in the kernel, which we didn't have before, and most others don't have either. Which means, well, the two states together perfectly describe one flow, like one TCP connection. And many subsystems in the kernel do some kind of state keeping on their own. For example, the TCP and UDP stacks. Well, they have to, of course. Others don't, but could profit a lot. And namely, that comes a few slides later. So we start invading the TCP and UDP stacks. Weird code. Obviously, they have to keep track of connections. So they use so-called protocol control blocks, or short PCB, prefixed by the address family. So we get in PCBs. Just mentioning that because you'll fall over that term a lot of times when you actually look at the code. And we just use our PF state key to keep track of them. So that's the PF state key again that we looked at before. Yeah, before it was nice exec poor, now it's just a struct, but still the same thing. We just add a pointer to our PCB. Now, before searching for the PCB ourselves in the TCP stack, we check the state key, and if it's set, we skip the lookup if it has the pointer to the PCB set. Code, again, pretty easy. If it's set, just take the pointer. When we had to do the full search, we tried to link it to the state key, and the only thing I have to point out here is that we do it both ways. We put a pointer to the PCB into the state key, and we put a pointer to the state key into the PCB. Why? Because, not shown here, when one of them goes away, of course the linkage has to be broken. Otherwise, we have an invalid pointer and the kernel crashes. Yeah, been there, of course. So, that's what I was going after before. The routing code could profit a lot from this notion of flows. Right now, we have to do a route lookup once per packet. And especially on full table BGP routers, that hurts. I mean, you have like 270,000 routes in your kernel at least. By the time I come back, it's probably 280,000. It grows. It's insane rates right now. And the idea is, this stuff is not implemented. The idea is to store a pointer to the route in question in the state key and skip the lookups. should give a really good performance gain, also help our caches a lot because we don't access the routing table all so often. So other stuff has a chance to stay in. There's a little tiny problem, unfortunately. It wouldn't be fun otherwise, right? Routes changing is actually not a problem. But they can go away. And this is the most complicated case, more specific routes could be added. But we can do it, of course. Solution, routes just must not get deleted. Sounds simple, isn't. Instead, when they would be deleted, they are flagged invalid and removed from the table. But they still exist, so pointers to them are still valid. And when trying to use a route from the pointer in the state key, we just have to check this flag, and if it's invalid, not use it, remove the linkage, do a new lookup, and decrease the ref count on the route that we hold the pointer to or add the pointer to, and if that goes to 0, we can finally get rid of it. That leaves the more specific problem. Example, assume your destination is 10.0.0.1, and the route lookup that you did gave us the default route back. So we link the default route into our state key. Now, somebody inserts a route to 10/24. That would be the right route to use, then that route is the one we would get when we did a lookup. But since we have the default route and it's still valid and the state key points to it, we are going to use it, and this is incorrect. There's a solution for that, of course. Before we insert the new route, the 10/24, we do a lookup. Actually, it doesn't have to be a separate lookup. We can do ugly games in the insertion routines, but that doesn't matter. So we will find the less specific route, in this case, the default route. That one, we have to remove and flag invalid and insert a fresh copy of it. So the content's still the same, but it's different as in it is not flagged invalid, while the original one that still exists is not in the table anymore, but flagged invalid. After that, we insert our new route, and due to the default route being replaced by a copy, the state keys now point to the old copy, which is now flagged invalid. So they do a new lookup and eventually find the right route to use. That's the plan. If anybody wants to implement that, be my guest. Still looking for somebody just doing the part in route.c and radix.c. That's code I don't want to touch. Again. So, now to something completely different. PF has this wonderful TCP connection tracker following a paper by Guido van Rij from 2001, I think. First it looks at the TCP flags like SYN and ACK and all that stuff to forward the PF's state like established or being torn down, stuff like that, as required. The other main thing it does, it verifies the TCP sequence numbers against the window. This, of course, cannot work when your machine only sees half of the connection. What I mean with that, traffic from A to B goes through a firewall, but the return traffic from B to A takes another route. This happens, is perfectly valid. You don't want it in your local net, but on the internet that's normal. So the more central you want to place a firewall, the more issues with that you will have. And the problem why that cannot work is that PF doesn't see the window size announcement, so it has no idea how big the windows are and thus cannot effectively match the sequence numbers against the window. So I implemented a so-called sloppy tracker. I had another term before, but Theo insisted on sloppy, and I think it's a good word for it. It does the bare minimum. It's just looking at the TCP flags, and it completely ignores sequence numbers. Another warning is in order. Do not use it unless you are really in this specific situation where you only see half of the connection. By doing that, you give up one of the strongest strengths of PF. Like the sequence number tracking is really important. So don't use it unless you have to. The full-blown tracker does much more than the sloppy one. They share the first 60 or so lines of code, and then the full-blown one does a lot more than the sloppy one, which just returns. So to give you an idea, it's 326 lines of code versus 69. As mentioned, you don't want to use it on your firewall. It's for other cases. But for forwarded connections, it should suffice to do the sequence number check on one side. We don't have to do it inbound and outbound, right? So the term auto-sloppy came up. We can use our shiny new state key linking. When we establish the linking, we can mark one of the two states on one side as sloppy because the other side will do the sequence number magic. And that should be faster, right? Well, it's slower. That was surprising. I didn't know why, so I just benched the full-blown tracker on both sides versus the sloppy tracker on both sides. And of course I expected the sloppy one to be faster, but there's no difference at all. Like nothing. So why? The full-blown one is doing so much more. Like you should look at the code. It's doing a lot of work. Why is it not faster? The limiting factor, our performance limiting factor here is not CPU cycles. We have, and this is on a slow box, I might add. We have plenty of CPU cycles. Our limiting factor is getting the data from memory. So while we wait for the data from the memory or for the caches with the sloppy tracker, the full-blown does more work, but, well, the sloppy one will just burn the CPU cycles and the full-blown one uses them. So why not use them? Next question, why is full-blown side on one side and sloppy on the other side actually slower than using full-blown on both sides? The explanation before is good for they are equally fast, but why is it slower? The theory we have is that it's instruction cache trashing. We cannot prove it. Well, maybe we could with this performance counter thingy. Whatever, we don't have that, so we cannot prove it, but that's the theory. The lesson to learn from that is that having small code helps because, well, it keeps your instruction cache out.
Petro size is
Petro size
tiny.
code.
That's not
Petro
small.
size is tiny. It's smaller than small. And needless to say, the auto-sloppy code went directly to dev null. That's it pretty much. Last week we had another network hackathon in Basel. That's material for a future talk, somewhere in the venue, somewhere not necessarily close to you, but I'm sure you fly around the world to see me talking again. I'm sure you do. Time for questions. Yeah.
What was the overall speed up from beginning to end?
I don't know.
Okay.
The auto sloppy code would be on a higher performing motherboard with better Ethernet interfaces that doesn't have such a critical bus limitation like the Circus does.
My test victim is actually not a Circus. It's a box with a Pentium M. I love it because you can scale down the CPU frequency to 70 megahertz. Getting a fastbar congested is actually not all that easy these days. So what you want to say is the effect of the cache trashing would not be there on a faster box.
I'm asking, did you test that?
Yes. You cannot measure a difference. So either it doesn't pay out or it makes you slower. So in the end, it's not worth it. That's what it comes down to.
This is simple and stupid, but to avoid trashing the odd cache, it would be impossible to make
I
this
can't understand you.
Sorry. This is simple and stupid, but to avoid trashing the odd cache for the sloppy tracker, it would have been possible to make it just a different code path through the full tracker. Since
Probably.
the same.
So you're saying we should share the code so it's the same code and we don't trash the cache.
If you're doing the sloppy check.
We could probably do that, but as outlined before, the sloppy doesn't save anything. So even if we get it for free, it's pointless.
How recent of work is this, and where is it going?
Okay.
When did this go in, or is it going in, or?
Most of the stuff I talked about here is in free. The route lookup code stuff is not written. The stuff fact in Basel sits on various laptops because we're close to release and kind of committed yet. Yeah, so all the other stuff is in free actually. I might add that lots of that stuff, the design of the state table is like 4 years old. So Ryan and I came up with that on a ferry ride somewhere in Canada. And it took us 4 years to, well, the magic 4 years are back. But opposed to TED, we didn't Slack for 4 years. We had to do so many little changes to like prerequisites to fulfill the requirements before we actually could do that. So you might be able to imagine the feeling when you finally do what you wanted to do for 4 years because all the other hindering factors are out of the way. That was really, really great. And we're not done yet.
Have you guys looked at some of the routing, the forwarding structured stuff that Linux people have been doing in the last couple of years? There's been a whole bunch of research that Linux guys are doing in fitting like entire internet bits in small amounts of RAM.
Well, I didn't.
You did?
The goal is to not have to consult the routing table all that often anymore. That said, there's another developer who is looking at that.
Right.
So it might happen. We don't know. Yep.
To follow on with what Adrian was just saying, I'm a little bit concerned about your comment about flow caching being a good idea. When most Cisco and Juniper in particular have concluded that that's not a good idea, even in software-only router platforms.
Because they don't have it under control. What they miss... really, what they miss is the abilities that PF has to fight the state table exhaustion issues. And they don't have those. And they kind of cannot have those because the router admins cannot understand what it's doing.
Well, no, the big difference here is they were doing their development on... They ditched the flow cache 10 years ago on hardware where they had to they were micro-optimizing on their MIPS and so on platforms.
And then the 6800s.
Yep.
Well, yeah, I mean, then the MIPS stuff was new and coming in, right? And these days, for the traffic flows they were doing back then, normal PCs can handle that. But the thing that some of the FreeBSD guys are playing with forwarding optimization using flow labels for doing fast TCP state lookups. So they don't have to do an entire lookup for every packet if they can match it to an existing TCP session, which works great if you're a PC, which is terminating lots of TCP and it sucks for forwarding.
Of course.
The big difference here is if you have a very small view of the internet, then flow routing works because the number of prefixes you have, the number of varying prefixes that packets are coming from and going to is small. When
That's
you're doing
true.
it on the internet scale, which is why they ditched flow caching, was because
That's true.
they couldn't hold all of that in RAM.
Yep.
And so they've done, again, this comes back to the Linux related question is those guys tried fitting all of that into L2 cache, a fraction of L2 cache, so that they could just ditch all the flow stuff entirely and say, well, it's irrelevant because we can do the lookups in one or two misses.
The very relevant point here being we have the state anyway. Like if you don't turn on PF and don't do the stateful firewalling,
Then you don't. Okay,
it just falls back to the other case. So the flow-based stuff or the state key linking-based optimizations are really just that, optimizations, and they're not mandatory. So if you don't want stateful or can't handle it for some reason, just don't turn it on. So I guess that's it. Thank you.